circuits. The purpose of this lab is to observe key hops, loop rule, and the junction rule in a simple circuit, and then we'll also look at charging and discharging a capacitor. So our fundamental principles are the conservation of energy and the conservation of charge. And in a slight preview, we saw that the potential difference increased across the batteries and then decreased across the resistors as expected. And that the experimental values that we found are very similar to the ones listed on the labels for the resistor and capacitor. So there are the three equations that we used that were listed. The first is Kirchhoff's loop rule, which says sum of voltage is zero, and then also the junction rule, which is the sum of current is zero. And then we also use the fact that for a simple circuit with a resistor and capacitor, this is the voltage as a function of time. And the reason we do this is because we're looking at a macroscopic view, so the back box approach is appropriate. And then also when discharging resistor, we have this formula of Q over C minus IR equals zero. So in solving that differential equation, we can solve for time, or we can solve for delta V in terms of time. We have a couple of assumptions. The first is that the potential difference across each battery is 1.5 volts. The wires and ammeter have negligible resistance, and that they're both accurate. So for the first experiment, the system is the battery, wires, resistors, and ammeters, and there weren't any surroundings to consider. There are initial conditions, so we just connected the battery and the resistors in series, and then measured the potential difference across each component, and then also the current at the end. So as you can see across the battery, the potential difference listed there is 3. Across the 47 ohm resistor, it's around 1.995, and across the 100 ohm resistor, it's around 2 or 1.945. So using these values, these can be graphed, showing how across the battery it increases and then decreases to around 2 volts across the 47 ohm resistor, and then back down to 0 at the end. So then we also used the values that we calculated for current, which was 0.02 amps, to find the expected resistance. So we just took the voltage and divided it by the current, and we found that for the capacitor, for the 47 ohm resistor, it's a typo, it's 49.75 ohms, and then 97.25 ohms for the 100 ohm resistor. For the wires, it was zero because the measured voltage across the wires was zero. For the sixth experiment, the system was a battery, the wires, the light bulb, and the capacitor, no surroundings. And the only difference is the capacitor was 1 Faraday, and the light bulb is 10 ohms, and then 20 ohms. So for this, we just connected the battery and light bulb in series to charge the capacitor and observe the light bulb. And then we discharged the capacitor by essentially flipping the switch in the circuit, and then we just measured the charging and discharging time. So there they are listed. Notice that it took longer for the 20 ohm light bulb system to charge up, but the charging and discharging times were very similar. So we also calculate the expected RC, which is just resistance times capacitance, so it's 10 seconds. And then we also use the formula from before, knowing that the final potential difference is 0.66 volts, to calculate for the expected RC. So as you can see here, we got 9.25 seconds for the 10 ohm light bulb, which is very similar to 10 seconds. And then for the 20 ohm light bulb, we got 22.7 seconds, which is very similar to the 20 seconds which we expected. So here it is. The error, very similar, only differed by 2 or 3 ohms for experiment 1. And for experiment 2, we only differed by around 1 or 2 seconds. And the reasons for this are just human error or differences between the labeled and actual values of the resistor. So if we were to use no resistor in the circuit, then the charging time, would it make sense? Because you can't really divide by 0. But as you go to 0, if you take the limit, the time to charge also approaches 0. So in real life, the time to charge would be very small, but it would actually still be defined because it's not possible to have a wire with zero resistance. Like wires themselves actually have a little bit of resistance anyway. And then when we actually did it, the measured time was around 1 second, even a little bit lower. And it's different than the predicted time of infinitely small because the resistance is never actually zero. So some conclusions are the potential difference increased across the batteries and decrease across the resistors proportional to the resistance. And that the values that we got were very similar to the ones that were actually listed on the resistor and the capacitor. And then also the potential difference across capacitor does change at an exponential rate with time when it's charging and discharging. We showed this by taking the logarithm. And lastly, that the RC constant of the circuits were around 9.25 seconds and 22.7 seconds. Thank you.